Hey guys, so this is my first YouTube video and I have chosen this one as my first upload because it's the most relevant subject in my work. I work at a solvent recycling and production company and ethyl acetate is our main product. The purpose of this video is to show you one of the industrial routes of producing ethyl acetate and opening a discussion about various ways of producing esters. So ethyl acetate is produced mainly by the classic Fischer esterification reaction, which reacts an alcohol with carboxylic acid in presence of a strong acid as a catalyst and produces esters and water as a side product. The esterification reaction is an equilibrium and the reaction stops at around 60% yield. To increase yield, we can either add an excess amount of one of the reagents or remove one of the products or do both. So I decided to use the equivalent of 1 moles of material. So I'm weighing around 63 grams of ethanol. This ethanol is an industrial grade sample and has 90% purity. Molecular weight of ethanol is 46 grams per mole and we need 12 grams of ethanol in excess. So that adds up to 63 grams. Acetic acid has a molecular weight of 60 grams per mole and my sample is almost 100% pure, so around 60 grams would be enough. Acetic acid acts as a limiting agent here and we can calculate the yield of our product. By boiling and distilling the reagents, we can separate out a mixture of 80% ethyl acetate, 10% water and 10% ethanol as a tertiary azeotrope. This would increase the yield from around 60% to almost 95%. Sulfuric acid here is used as a catalyst and we need around 10% of the amount of acetic acid, but my sulfuric acid is not very pure. As you can see, it has a little bit of a brown color, so I use another 4 grams of it, 10 grams in total of sulfuric acid as a catalyst. So as you can see here, I used an Erlenmeyer flask and a Claisen adapter for my reaction setup. The Claisen adapter lets us add more reagents midway during the reaction if we want to get a more sizable product. You can see here the Claisen adapter, the Vigro or distillation column, another Claisen adapter, a thermometer to give us the temperature of the overhead product, a Dean Stark apparatus with a valve, and a reflux condenser with cooling water pumping through it. So this is the overall setup. We're gonna connect the boiling flask to the mantle. So we've put a heating mantle below the boiling flask and we're gonna try to boil the mixture through the distillation column to get the tertiary azeotrope of ethyl acetate, ethanol and water. So the Dean Stark apparatus here helps us reflux some of the overhead product. The way the Dean Stark apparatus works is that it will reflux through the arm here, through the distillation column, and it will keep the temperature of the top of the column fairly constant. So the tertiary azeotrope boils at around 67 degrees Celsius, so we need to keep a steady temperature at the top of the distillation column. So overall, this system will give us a semi-continuous process of distillation, and let's see what happens. So it's been a while now and the mixture has started to boil. You can see the droplets of condensate in the column. Each of these sets of spikes are a separation stage that helps us get a better product. The temperature is around 67 to 68 degrees Celsius, which is the temperature of the tertiary azeotrope of ethyl acetate, ethanol, and water. Beanstalk is refluxing some of the mixture. Actually, here it's refluxing all of the product. It's a total reflux. So we do a total reflux at the beginning of the reaction at about 45 minutes to reach the equilibrium, which is the 60% mark. After a while, we open the valve of the Beanstalk apparatus to collect some product. The degree of the collection of the product, the ratio of the product to the reflux is indicated by the temperature of the overhead product. So we have collected some more product. It took an hour to get around 70 milliliters of product. But we don't want the temperature of the overhead product to reach 70 or even 69. And the reason is that the 70 degrees mark is actually the binary azeotrope of ethanol and ethyl acetate at 70% ethyl acetate and 30% ethanol. This would decrease the yield of the reaction because some of the reagent, which is ethanol, would appear in the product and would be left out of the reaction. So after 2 hours of reaction and adding 1.5 moles more of the reagents, here we are 194 grams of product, which is crude product, of course. So we're gonna add our crude product to an airline flask. Then we're gonna measure some calcium chloride and add to it. Calcium chloride will help with the separation of ethanol and water from ethyl acetate. One step washing with calcium chloride will give around 95% purity of ethyl acetate, less than 1% of water, and around 4% of ethanol. So we need around 3 to 4% of calcium chloride so that calcium chloride can make a liquid layer to separate out from the ethyl acetate. The liquid layer will contain water and ethanol and a little bit of our product, ethyl acetate. So I poured all the mixture into a beaker for a better visualization, and I've put it on a stirrer. It has been mixing for almost an hour. You can see the layers of calcium chloride, ethanol and water separating from our product, and we're going to separate it in a bit. As you can see here, I have added all of it to a separation funnel and I'm waiting it out to separate. We're gonna separate the top layer as our product and filter it because it's a little bit murky. So this is our product, our dried and purified product. It's just a little bit cloudy. We're gonna put some cotton in a funnel and filter it. If you're wondering why I'm using a plastic funnel, the funnel is made out of polyethylene, which is fairly resistant to ethyl acetate. So you can see our product has cleared up. The cloudiness is because of some of the calcium chloride particles that are very fine and they just somehow disperse through the product. You just have to filter it out. So now I'm going to check the purity of our product with a pycnometer. This is a 25 milliliter pycnometer equipped with a thermometer and it is calibrated. So if you have the equipment, it's a very good method to check the purity of the product by checking the density. As we have dried our product, the mixture is a binary mixture of ethyl acetate and ethanol, which has recorded data of density, and you can find it on the internet. So the way the pycnometer works is that you have to cool down the temperature to lower than the temperature of the calibrated thermometer, which is 20 degrees for mine. And then after you have cooled it down, you're gonna pour it all down into the pycnometer. To determine the density quantity of our mixture. So what I do here, to not to splash a little bit, is to... And what we need to do is to push down the thermometer into the pycnometer to spill out the excess of the solvent in it. You can put the thermometer in a beaker to prevent splashing. So we're going to read the temperature. When it reaches 20 degrees, which is the calibrated temperature of this pycnometer, you're going to put the cap on, dry it off, and take the weight. So this is the gross weight of the pycnometer. We will subtract the weight of the empty pycnometer from it. This will yield us the net weight of the solvent inside the pycnometer. Then we will divide it by the calibrated volume of the pycnometer. This will get 0.899 gram per cubic centimeters, which is a 98.5% pure product. So now we're going to measure the residues of the reaction. The residues must contain some water and the sulfuric acid we added as a catalyst. So the esterification reaction produces 1 mole of water per 1 mole of ester. So for 2.5 moles of ethyl acetate produced, we have 2.5 moles of water produced. The produced water is around 45 grams, and we removed some of the water in the azeotrope during distillation. There was around 10 grams of sulfuric acid, and that adds up to around 45 grams in residue. Thank you for watching this video. Please leave a comment to talk about the process, share, and subscribe.